Well, thanks to everyone for inviting me to come speak to you today. Thank you, John. Thank you, members of the search committee. Thank you, Brittany, for organizing my trip here. It's been really great meeting everyone, talking to the students yesterday. Yeah, it's been wonderful. So today I'd like to talk to you about human demography and evolutionary ecology in the Northern Great Basin. But I'd like to start by saying that population growth, as we all know, is one of the greatest challenges that we currently face in our societies today. And I think that this is an area where archaeology stands to make one of the greatest contributions it could potentially make to current societal issues. And the reason for this is that we have a limited time depth when we consider historical records. And archaeology can provide us with this unique long-term perspective on population growth and adaptation to environmental and climate change. So I approach everything on a macro and a micro scale, because as these arrows show, what we do in a local scale affects what happens at more global scale processes. So we have to always think about, we have to always consider the local in context to the global. And so currently I'm co-leader of a group funded by Past Global Changes. That's funded by the Swiss Academy of Science, the National Academy of Science, and the Chinese Academy of Sciences, to run a group called People 3000, which stands for Paleoclimate and the Peopling of the Earth. We are working in local areas. We're bringing together people from 15 different countries across 4 different continents to look at these teleconnections between population growth and human environment interaction over long-term scales. So my question I want to focus on today is, how does human population growth and adaptation to climate change in the Snake River Plain and the Owyhee Plateau over the last 14,000 years compare to the rest of the Great Basin? And I'll start off by introducing a new framework for research on human paleodemography and evolutionary ecology. I'll then move on to showing new research on 14,000 years of human population ecology in the Great Basin, and how that highlights and necessitates a need for new research, for intensive research in the Snake River Plain and Owyhee Plateau. And then I'll close by talking about what my thoughts are for strategies of continuing the integration of contract archaeology, interdisciplinary research, and education at Boise State. So I'm going to start talking about this new framework that we have. And it all starts with fundamental population ecology of all animals. There's 2 basic principles of population ecology for any animal species. The first principle of population ecology theory is called the exponential growth model. And that is that for any species, if you remove environmental constraints being K here, and you're looking at population density on the y-axis and time on the x-axis. And then if you don't consider a local environmental carrying capacity, you will see population densities increase through time and continue to increase. The second principle of population ecology theory is the logistic growth model. And that holds that through time, populations start to increase, but they're limited by carrying capacity, local environmental constraints. When we're thinking of human systems, we have to break this down into two basic theories that go back to the 18th century and Thomas Malthus. Thomas Malthus proposed that human populations will always hit some sort of resource carrying capacity. So the logistic growth model. In the 1960s, Esther Bossert published a new population ecology theory arguing that actually humans, through population growth, as population increases, humans can innovate social and physical infrastructures and strategies for moving beyond, for increasing the carrying capacity of their environments. But it's complex, and these are not mutually exclusive models. So James Wood in 1998 proposed a combination of the Malthusian model and the Bosseropian model. On the y-axis, you have the total output of a human system. On the x-axis, you have increasing population size. This straight line here is the minimum amount of resources you need to sustain a population. What Wood proposed is that you can get increases in a curve of production. So a Bosseropian system, you can have innovations to create some sort of safe space here above your minimum carrying capacities. But eventually, you will hit this Malthusian point where you need to somehow increase your innovations and create a new curve of production. So how can we use archaeological data to understand deep time human population dynamics? Because these are models that have been proposed for all species. And humans typically have not been considered in this. And oftentimes it's because we lack the data necessary to do such. So while population has been one of the most important causal agents proposed for human evolution, we have used the archaeological record. We have been limited in what we have in the archaeological record to actually understand these deep time dynamics. And that's because estimates of population size in the past have typically been proposed based on floor size, floor area of houses, site size, midden volume, food abundance, or pottery sherd densities. Humans don't always produce pottery. We don't always excavate house structures. We therefore lack an adequate measure of population that can be easily and realistically compared between species. So one possible solution to that are radiocarbon date frequencies. It's having me admit people in the room. So in the 1980s, researchers proposed that we can use aggregations of radiocarbon dates through time, not as absolute measures of population, but as relative probabilities of human occupations through time. One of the pioneers of this was Mike Berry. The idea is that if we are excavating an archaeological site from the last 50,000 years from anywhere in the world, there's a good chance that we are using radiocarbon techniques to date the time of that human occupation. The basic principle on the x-axis, you can see 1,000 years ago to 11,000 years ago. So from back in the Paleo-Indian period, this is from the American Southwest, to 1,000 years ago. And here you see just the numbers of radiocarbon dates per 500-year time bin. The basic principle that this works on is that the more datable materials we have in the archaeological record, most likely there were more people to create that record that we date. So the idea is that in the late Pleistocene, the terminal Pleistocene in the Southwest, you had relatively high populations. It was colder then, it wasn't as rough in terms of environments, and you get a decline in radiocarbon date frequencies in the early Holocene and starting in the Holocene thermal maximum period. And then after about 5,000 years ago, in the region that Barry was looking at, you see increasing frequencies of radiocarbon dates, and then you see declines in dates. Now, why is this valuable? We're dealing with proxy data in archaeology. Every bit of our data is biased. There's always going to be biases in our data, right? This is the loss of datable materials through time, right? We just lose more materials through time. So the early iterations of this, we're not considering the various biases in these data sets. And a lot of the work that I do is focusing on the statistical measures to take those biases into account. If we're thinking about human-environment interaction, paleo environments are reconstructed through continuous time series data. If we rely upon typology such as the Clovis point, or such as the amount of brush structures that we have, or the amount of maize that we have, these are discontinuous measures through time. These are not continuous measures. So we want to think about environment interaction, human environment interaction. We need to consider the potential of these continuous measures, because that now we can actually start to compare apples to apples. So in 2014, Bob Kelly and I started working on a long-term National Science Foundation project to collect every radiocarbon date we could find from cultural resource management gray literature in the United States and from research publications. One of the greatest movements that we have in American archaeology right now is the fact that since the 1960s, cultural resource management, millions of dollars have been spent in generating archaeological data. Those archaeological data are oftentimes only accessed by regional specialists. They are held in data silos. So our objective here was, if we're really going to build an adequate measure of continuous time series data through time of human populations, this relative measure, then we need to start collecting these data. For just under $1 million, we have collected and released to the public, or are in the process of releasing to the public, $34 million of publicly funded archaeological data that might have never seen the light of day. These can be used not just by archaeologists, by biologists, ecologists. Okay, we're making this accessible. We're talking about bias. There is a lot more public land in the Western United States. Therefore, by law, you have to do cultural resource management work. We also have deflated sites. Sites are easy to find in the Western US. As we go east, we have more private land. We have more trees and land cover. Sites are harder to find, okay? So we have to be honest about the limitations of our data sets. And we have to start considering ways that we handle these biases. We have 102,000 radiocarbon dates. Now, we have to be realistic in archaeology. We're not dealing with petabytes of data, but this is about as close as we've gotten thus far in archaeology to big data. Now the challenge is figuring out how to work with those data. So what you see on the x-axis, on the y-axis, is a logarithmic scale of a summed probability distribution. So rather than use histograms, which were the early iterations, We also have to calibrate our radiocarbon dates. Folks, we're not transferring radiocarbon dates into actual calendar dates. So we've got to do a few things. First of all, we have to create a continuous time series from 15,000 or about 14,000 years ago on the x-axis to the present. So we're summing and aggregating calibrated radiocarbon dates on a calendar scale. And when we have this in a logarithmic scale, we see something interesting. We see that between 13,000 years ago and 6,000 years ago, this is highly linear. In a log scale, if something's linear, that might indicate that we're seeing exponential growth. So, question I had was, well, what is the growth rate? Can we capture a rate of annual growth from this time series? If it's exponential, we can fit an exponential model to these data. So in the light gray, you're seeing a 68% confidence interval. This is developed through bootstrapping. So we're already starting to take on the bias of the data, knowing that there's sampling bias, there's calibration bias. There's all of these problems that we have to be honest about. The black is the 95% confidence interval. So if something's falling in here, that's just a spurious peak trough. We can't say, oh, there was this increase of populations around 9,000, 8,500 years ago, and then they plummet. No, that's why we have to build these confidence intervals. But what we were able to do is that when we fit this exponential model, we can obtain an annual growth rate. From 13,000 years ago to 6,000 years ago, you see that the rate of growth, 0.4, 0.02, and it increases and declines. Our result was actually mind-blowing, and that is this. Our result is this, 0.04. So over 13,000 to 6,000 years ago, the rate of growth was 0.04. Here you have a study for all of North America. This is a data set that it's quite incomplete. Our work is filled in. Here you have Australian hunter-gatherers. But here you have early farmers in Europe. We have always thought that the reason why we have explosions of human populations on Earth is due to the advent of agriculture. Our results call this into question and show that actually hunter-gatherers are capable of growing at similar, if not greater rates than farmers. It can't solely be the transition to agriculture. And this is what drives my work. What features of hunter-gatherer societies not only make them resilient and highly resilient to climate change, but make them capable of growing these high rates? I think we've given hunter-gatherer societies short shrift in their ability to grow and create social innovations. So there was a response to this paper in PNAS by Bob Bettinger. And he proposed that we're just capturing an exponential part of the curve. That in Wyoming and Colorado, these purely hunter-gatherer populations that we were capturing, they hadn't hit carrying capacity yet. There were these Malthusian processes that would come into play, that we were only capturing the nice exponential part of the curve. Now we're looking from 13,000 years ago. This is the earliest entry of humans into Wyoming and Colorado. This was justified using one form of population ecology theory. And these are called ideal distribution models. So he explained that we were capturing what's called the ideal free distribution. And that is that you have habitat suitability on the y-axis, less suitable habitats, more suitable habitats, and on the x-axis you have as population increases within a given habitat. The ideal free distribution says that humans will always inhabit the most productive, the most suitable environments first. And as population increases, the suitability of that habitat goes down and reaches a point to where humans say, let's go to another area, right? The resource potential between habitat 1 and habitat 2 are equal. So effectively, humans can always bud off in new areas when they're colonizing these lands. However, there are two other ideal distribution models that were not considered in this explanation. And that is one called that really interests me, called the ideal free distribution with the Lee effects, effectively human cooperation. And what this model proposes is that when human societies enter this most suitable habitat, there are increasing returns to scale. Humans are cooperating, they're creating social infrastructures, so soft infrastructures, and hard infrastructures. Now, obviously, hunter-gatherers at this time, there's few hard infrastructures. So these are social organizational strategies where they are increasing their returns to scale, and you hit this point to where it decreases and groups start to bud off. There's a third model, which is ideal despotic distribution, and it assumes active territorial defense of a habitat. So it's similar to ideal free distribution, but it's not free. Humans are territorially excluded. This is the ideal free distribution, this dotted line. This is the despotic distribution. There is territorial exclusion, so humans are kicked out of the habitat at earlier rates than in the ideal free distribution model. Well, this is great, but how do we test this? How do we use our radiocarbon time series to investigate this problem? Because ultimately we're talking about Bosserapian systems versus Malthusian systems, the exponential versus the logistic growth curves. So we have to model this. We have to consider the implications of ideal distribution models. So this R1, R0, R2 on the y-axis is a spatial statistical measure of the relative clustering of things in space versus the relative dispersal of things in space. So the ideal despotic distribution assumes that groups, as population increases here on the x-axis, groups will increasingly disperse through space due to this territorial exclusion. Ideal free distribution assumes dispersal through different habitats as populations increase. But ideal free distribution assumes that groups will cluster for periods of time. There will be increasing returns to scale as populations increase. It hits this point, and then groups bud off. So what we had to do is figure out a way to transform a calibrated radiocarbon time series into a spatial statistical measure. So on the x-axis, you see 13,000 years ago to present, and you see this log, the non-log SPD, the summed probability distribution. So these are the frequencies of radiocarbon dates. And you see this exponential curve hitting a plateau, most likely a logistic curve. Populations, relative populations, declining around 2,000, 3,000 years ago, increasing and then decreasing. Now I want to put this on your radar immediately, this peak trough right here, because this is where the Snake River Plain and Owyhee Plateau become very interesting. So what we can do is we can use these measures of dispersal versus clustering. We can transform this SPD into a spatial statistic and show that actually it's the opposite of what Bettinger proposed. When humans enter these territories, they're actually more clustered in space. Think about Paleo-Indian big game hunters. They're cooperating to hunt species, right? There's no reason why there would be exclusion whatsoever. So actually, human population growth is a result of cooperation, increasing returns to scale. It's not these exclusionary mechanisms which are causing humans to explode as populations. So you see in these periods, and now this is where the Snake River Plain and Owyhee Plateau become very interesting. Now, while this is from Wyoming and Colorado, you get the advent of groundstone tool technologies. You get the development of broadening spectrum economies. Folks, increasing the amount of plant consumption in their diets, and you get the development of technologies to process those things. Now, I don't think that they're processing seeds. I think that they're processing tubers. And we are really excited. There's a paper that's currently in review right now, where rather than speculate what groundstone tools are used to process at this period of time, we can obtain starch granules directly from groundstone tools. And we have provided the first evidence that they were actually processing geophytes. Now, evolutionary ecology theory that supports it. Seeds have low return rates. Geophytes have high return rates. These are also highly predictable through space. You get the advent of pit houses at this period of time. So you get humans coming together on this landscape. And I think that this is very similar to what's going on potentially in the Owyhee Plateau and the Snake River Plain. Okay, so let's go to the meat and potatoes. We have been reconstructing human environment interactions across the Great Basin for the past 14,000 years. And this work highlights some really unique things about the Northern Great Basin. Okay, so there's a lot here. On the y-axis, you have the summed probability distribution. Now, you're wanting to look at this. This is our empirical summed probability distribution. This is the aggregation of radiocarbon dates from 14,000 years ago, or 12,000 Cal BC. So just add 2 years, you get to 14,000, or add 2,000, you get to 14,000, to the present. This is the entire Great Basin. What we have to do is we have to overcome these biases. It's not just enough to bootstrap, okay, like was done in the first PNAS paper. We need to fit some sort of a priori theoretically derived model to determine what is spurious in these peaks and troughs and what's actually a real signal. So what I do is I fit an exponential curve. This is the light gray. Again, the first principle of population ecology. Fitting this curve using thousands of Monte Carlo simulations enables us to develop a confidence interval here. And when the peaks are above the exponential curve, we know that that's a statistically significant signal. So the red represents, and we're using a 200-year moving mean in order to be as highly conservative as possible. Now, I'm happy to talk further at the end of the talk about the vagaries and the problems of the radiocarbon calibration process and why we do this, but this 200-year running mean is an important measure of conservatism with dealing with biases in our data as well. The red represents population booms, or higher than expected sizes of population across the Great Basin. The blue represents lower than expected. We are interested in the Younger Dryas, so the terminal Pleistocene, the Holocene thermal maximum, the 8.2 Ka event. So this is what the Pentagon has identified as the worst case scenario for the next 200 years of climate change. This occurred when the North American ice sheet melted off into the North Atlantic Ocean. This is the very end of basically glacially dominated climates on Earth. This is actually, like, people think that this is the transition to the Holocene. I actually think that it's this, because this represents a complete shift in the dominance and in what's creating climate change on Earth. Mount Mazama, so Crater Lake, that eruption, how did that eruption affect populations across the Great Basin? The 4.2 Ka event, this is the transition from the middle Holocene to the late Holocene. Again, this is represented in, people think that this is the collapse of civilizations in the Near East, in China, the Yellow River Valley, and the late Holocene dry period, the medieval climate anomaly, and the Little Ice Age. Well, the first result is that the Younger Dryas does not affect populations in the Great Basin like we think it does. The second result is that the 8.2 event, the thermal maximum, not affecting populations. The Mazama ashfall, surprisingly, it's not affecting populations. Maybe. The 4.2 event, the curve hits the exponential, no effect. The late Holocene dry period, something is certainly going on. And then we have this boom of populations during the medieval climate anomaly and a bust in populations in the Little Ice Age. Now, I want to stress that my group, looking at these records around the world, we're finding this boom-bust relationship regardless of the society, regardless of the economy. It's happening everywhere, except for the Snake River Plain and Owyhee Plateau. It's one of the few places that this happens. We know that climate change is more complex than that. We can't simply fold a global scale climate event over a massive space. The Great Basin, we want to think it's got this homogeneous environment, but it's not. If you've been into the Central Great Basin, the person I'm working with, Dave Thomas, excavating sites up at 13,000 feet, right? It's got a lot of variability. You can move from one valley to the next, and ecosystems are responding to climate change in different ways. So what we've done is broken this down. I know that there's more than 9 represented here, but we have 9 different floristic zones. Because what we've done is we've taken paleoenvironmental records from each of these areas to understand how the lakes area responds to each of these climate events versus the Lahontan Basin and its response versus the Bonneville Basin versus the Owyhee, the Snake River Plain. This is within the same area in the plot I'm getting ready to show you. Down to Tonopah, the Southern Sierra in front. We're trying to understand the variability of ecosystem responses and human responses across this space. This is a lot, but remember, the reds represent population, higher populations than expected with the exponential null model. The blue represents lower than expected. There is a lot of variability in the Great Basin. So this is the western sector, the lakes in the northwest and Oregon, the southern Great Basin, the Mojave Desert. On the east, you have the Owyhee Desert, Snake River Plains, down to the Bonneville Basin. You do not see red and red and red and red. Interestingly, in the middle Holocene, you see what we're thinking is some syncopation. The idea is that across the middle of the Great Basin, you have what's called a dipole. And a dipole shows that there's different responses to climate change events in the northern Great Basin compared to the southern Great Basin. But I want to bring your eyes to Owyhee Desert. So as you can see, we have a smaller amount of radiocarbon dates here. That makes our confidence interval wider. Okay, because we have to build in more noise. We have to consider more noise in this record. But out of these 8 time series, we can have these significant peaks and troughs, right? Significant peak, significant trough. But there's only one area that is not statistically significant from the exponential growth curve. Again, from the first principle of population ecology, and that is the Owyhee Desert, and Snake River Plain. All of these other records show potential logistic increases, declines. It's not fitting these exponential models. Therefore, we need to use something like multi-logistic models. And that's something that I'm currently working on, is how we can break these down and really start to get at these changing. We can use multiple different types of population ecology models. Why does it fit the exponential model in these areas? Why do you have such a good fit? Now bring your eyes to the early Archaic period and the late Archaic period. First of all, you get the broadening spectrum of economies. You get the development of groundstone technologies. Remember, in the Wyoming plots, talked about geophytes, roots, right? These are having multiple predictable, seasonally predictable patches of resources that you can map onto. And I think that has a big story to tell in the relative resiliency of these periods of time. You see one event here, okay? This blue. Mount Mazama, no doubt affected ecosystems in this area of the world. It's nearby. And you see a lag effect in these populations right here, right? So it takes about 600, 700 years. So we're looking at ecosystems, forests being damaged, animal populations potentially being damaged, and humans are responding to that. Are they moving south? We don't know. They're definitely moving around. And again, that's what's interesting about these things. Here you get the development of houses. You get an increasing permanency of place in the middle Archaic record of this region. What's interesting is that this is the only thing that could be a switch to a more a logistic growth model, right? Something is happening where you see this increase of populations. They're not moving above the confidence interval, right? So this is some noise right here. But you do get this decline in the late Holocene dry period. Well, remember I said that the way we need to think about how exponential growth of human populations interacts with logistic growth is the ability of populations to innovate, to create innovations to adapt to their environments. You do not see a boom-bust feature in the late Archaic period here, okay? Development of perishable technologies, development of pottery at periods of time. Now, it's these technologies that I want to focus on. We need to break down these records because ultimately these are coarse-grained measures which develop hypotheses that have to be tested on more micro scales. And I have slides representing the methods that I use that I'm happy to discuss in the Q&A period. I've got a lot of Q&A slides. I can talk specifically about my procedures to develop high precision chronologies that test this. Because again, coarse-grained measures that we can only think about in terms of centennial scales, but we can't get to human lifetimes yet. But I think we can potentially. As I said, in starting around the world, we see this boom bust. The boom, the bust. Here we see the bust, the boom. That's interesting. Bonneville Basin, pesky farmers. This is the Fremont tradition. This is another group that I study. It's one of the few examples that we have on Earth of hunter-gatherers adopting agriculture, and it didn't work out so well for these folks. And I want to understand why it didn't work out so well for these folks. So again, lots of supplemental slides. So this sets up the problem for my work that I would like to do in the Snake River Plain and Hawaii Plateau. Why such relatively stable populations compared to the rest of the Great Basin? Well, as Mark Plew has said, Aboriginal interaction with the environment over nearly 12 millennia has produced a range of material culture and lifeways which attest to the dynamics of the Native American pattern and mirror the diversity of early settlement and modern utilization. Now that excites me because we have a new suite of archaeological science methods that we can now use to further investigate that result. So how would I plan on continuing the integration of contract archaeology, interdisciplinary research, and education at Boise State University? The first thing is that I think for training students in CRM, we need to train theory-driven and model-driven approaches to our training. And this not only deals with contract archaeology, this helps direct the field school that I would like to develop. I've been in communication with the BLM folks. They have created a very interesting and highly profitable, in terms of directing archaeological field schools, a probability model of the sensitivity of certain regions to finding archaeological sites. So what you're going to notice is the red. The red are very high, the red and the orange are very high probabilities of encountering archaeological sites on a landscape. The blue and the green are low probabilities. Here you see an example of an inlay. My field school that I would like to direct will be guided by this. We will communicate with the BLM. We will focus on one of these areas that has, I want to focus on an area that has an interaction of this yellow, low, moderate probability. These could be canyons really in the river, right? So we might not be able to survey some of these areas. But we spend 2 weeks going out into the field. Students learn paperless recording strategies. We learn how to walk transects. Students learn how to use GPSs. And we learn how to record sites. So basically, in CRM terminology, phase 1 training, phase 1 processes. If we're lucky, which we probably will be, we can move to phase 2. So the next 2 weeks of the field school are going to be test excavations, doing a 1 by 1 meter trench, so telephone booths. High sensitivity zones where we find sites, students find sites on the surface, we dig some telephone booths. Now all of this is in cooperation and communication with the BLM, right, from the beginning. Right? In the last 2 weeks are going to be developing lab methods. Oftentimes field schools will just leave you in the field. You leave the professor, take the artifacts, you fly back to wherever you came from. I would like to build an nationally and internationally competitive field school. And how we make ourselves unique is that we bring them in and teach them how to wash artifacts, process artifacts, develop database entries, relative databases. We also have something great here at Boise State, potentially, and that is the potential for building an archaeological science component. Students do not ever see from materials being identified in the field to being excavated, to being brought and processed in the lab, to being taken to an archaeological science lab, and for instance, used for isotopic analyses. So I see CAS as a teaching tool for training cultural resource managers, cutting edge, quantitative and interdisciplinary scientific techniques. That predictive model leverages CRM work in a synthetic manner, and we can develop theoretically guided research designs based on that. Writing skills are highly important in the way that I teach students. My students have to learn how to write bids. So my archaeological science class, students learn how to write CRM bids. They learn how to budget technical analyses, so geochemical analyses of pottery or obsidian flakes or whatever. Or they write an NSF doctoral dissertation improvement grant. This teaches students how to write directed, problem-focused writing, but also cutting to the core of developing budgets that are responsible. Because if there's anything that CRM needs right now, it's developing some responsible budgets, okay? That strategy of teaching helps to break down the black box of instrumental techniques that are used. Oftentimes archaeologists say, oh, let's just do some isotope analysis. Let's send it off to the lab. Why? What's your question? What do you hope to gain from that? This costs a lot of money. It's a lot of time and energy, right? And that's what my teaching is focused on. Enhancing field and lab training techniques, links with College of Western Idaho, right? So an important feeder school to Boise State, reaching out to those folks, right? Having them come out into the field with us, cooperating with us. This is important for our recruitment in this program as well. And leveraging CAS work for external research funding proposals. I have a supplemental slide that can show how funding from the National Park Service has led directly to National Science Foundation proposals. And I'm happy to show you those slides in supplemental. So my teaching roles, undergraduate, I'm able to teach all the archaeology courses that are already on the books here. I've looked through your course catalogs. I have the potential to develop courses on archaeological science, archaeology of Western North America, or we can call it Intermountain West, world archaeology. In the graduate program, climate change archaeology, I'm ready to teach. However, it might be a better title to call it integrative paleoscience for the EEB PhD program, because oftentimes archaeology is removed from paleoclimate, paleoecology training. Anthropological perspectives on conservation and Bayesian statistics in the paleosciences. I have 3 projects currently out with the NSF in review, $2.6 million of external research funding with 3 different NSF programs that can create funding for PhD students, master students. Really, the inertia of my research program is already set in place. And I have slides on each of these projects that I can go into in the Q&A. The first is with the NSF Dynamics of Integrated Social Environmental Systems program. It's titled Collective Decision-Making and Infrastructural Design Principles for Coping with Deep Uncertainty in Social Environmental Systems. I see this as fitting in very well with the EEB PhD program, as well as Human Environment Systems departments. And I can explain more about this later. These are huge global comparative studies. We're doing behavioral experiments in the lab, students playing games. So cognitive experiments, as well as what we're calling natural experiments. Our NSF archaeology program, hydroclimatic variability and the evolution of socio-ecological complexity in dryland farming communities. This is my Fremont work. What are the environmental constraints on human cooperation? What are the environmental constraints on the development of social economic inequalities in societies? And lastly, I'm really excited it could feed in well to the data science degree certificate program, and that is to the NSF Human Networks and Data Science program on the Interactive Radiocarbon Archive and Paleodemography Explorer. These radiocarbonates are great, but they're not integrated with the reports. We can't build multiple proxy approaches to paleodemography, and we have to build multiple proxy approaches to paleodemography, and also the potential to do some high precision stuff. Again, I'm happy to talk about these projects, and I have further slides on them. So what do I plan to do during the winter to build my lab? There's a few pilot studies I'd like to start immediately. The first is putting everything into a GIS. To train through this, have students do spatial temporal analyses of sites in the Owyhee Basin, Owyhee Plateau and Snake River Plain to understand dispersion, clustering dynamics through time. Developing high precision chronologies to investigate possible pre-Clovis occupations of diversion Banana Cave. There are seeds from Hearth 1 preserved that are curated, that are just ready to date immediately. That's a big question and a big debate in this part of the world, is about pre-Clovis, how early were humans here? We need some high precision approaches to this problem. The next is to do starch grain analysis on groundstone tools to understand these direct consumption of root vegetables. This can go on the back of the pilot work I've already conducted, similar situations in Wyoming. Developing high precision chronologies and stable isotope analyses of freshwater mussels and other legacy faunal collections that we already have, focusing on diachronic change through the Archaic. Remember I said there are these innovative periods happening, right? Why are they fitting this exponential growth model? And finally, I think that there is a lot of potential to develop studies and high precision chronologies of perishable materials, such as the nearby Shellbach Cave and the Column Bay Creek Rock Shelter. So thank you very much for your attention.
there a way the virtual audience can ask questions?
Yeah, no, they probably can put them in chat.
Yeah, it looks like maybe there's something in the chat.
Look more.
I don't.
More. Up to the right. Yeah.
Yes, I think I got yes when people ask if they could hear me.
I have a question if there's none coming online. So what are the limitations and why on high precision dating? Do you have a lack of material to date available, or just the lack of excavation, or where's the limitation?
What is getting in the way of the potential for high precision dating?
Yeah.
Nothing. I mean, the only thing that gets in the potential in the way for that is with the perishable materials, there might be some cultural rights and cultural sovereignty issues.
Yeah.
You know, we sometimes face that when we're dealing with like public museums. You know, with certain tribes, we might not get the permission to date those things, and so that's a realistic thing that needs to be considered. Is you know, we may not be able to sample everything available. Periods of time.
This is a question not about your research, but archaeology, anthropology, and inclusivity in general. How should archaeology and anthropology sort of try to be more inclusive going forward in the past year that we've had? What work do you think needs to be done, and how do you think we should achieve it? And I should preface this a little bit with, we have a lot of students here who are non-traditional sort of students. Like how does anthropology and archaeology be really inclusive to this diverse student population that we have?
It's a great question. I mean, you know, there's a lot of lines of this. So the first is that I try to incorporate as many non-Western perspectives in my classes. So I use a lot of multimedia videos. So if I'm talking about the spread of maize agriculture, maize horticulture to northern, the Colorado Plateau, my students are watching videos about Hopi, talking about Hopi corn. In my conservation class, my students learn, I mean, a key component of my conservation class is they read the Intergovernmental Panel on Ecosystem Services and Biodiversity document, and we basically critically assess that to see the lack of anthropological information on indigenous ecological knowledge and how that's included in there. And so I include as many different non-Western perspectives to therefore decolonize the classroom. That's one sense. The second is I feel like, you know, my best students have always been mature students, non-traditional students. In Wyoming, I have experience. We have a huge, like, former military members right there. And I'm driving here. I see that you all do too here. They're so serious and they're so, like, they're the best students. The problem is that professors are oftentimes not considerate. Like, it's one thing to be inclusive and to say, hey, everyone come into the university. Well, what are we going to do to keep them here? We think so much about inclusion. We don't think enough about retention. So I do a few things. I love to employ non-traditional students in my lab, right? Giving them GAs. They have top priority on things like that. And another key thing is that, and especially at the undergraduate level, I have 3-day due date windows. I think it's highly unrealistic for me to think that a non-traditional student is going to work the same way I did, being a privileged white kid who went to undergraduate when I was 18 years old, right? It's just, they have kids to go to. They have full-time jobs. So flexible due date windows. The second thing is that open source programming. It's really bad to teach statistics in non-open source settings because they don't have a community to go to. When they go back home, they put their kids to bed, right? They're going to go on the Microsoft website and learn how to do, you know, it's unrealistic. When you teach R, right? When you teach QGIS, they have a huge community they can go to. right, to get answers on their questions. When I teach Bayesian statistical modeling, chronological modeling, I direct my students to the Oxcal listserv, which is the program I use. And the last thing is this. We have a legacy of pointing our noses down at non-traditional groups. We are anthropologists and we want to understand cultural diversity, but we want it in our terms. We dictate to folks. I have 2 examples that I'm really excited about. The first is that I have a student who's a member of the Pawnee Nation that came to me and said, I want to use these methods to try to understand Pawnee cosmologies and creation stories of the spread of northern Caddoan groups onto the Great Plains. And I love that. It's super interesting, right? Being able to, instead of having this conflictual relationship between the archaeological record, right, and ethno-historic groups, you can actually define your archaeological analyses based on ethno-histories, right, cosmologies. So we use that to direct our research. Well, I said, when is the origin story of Pawnee? 1450, 80, 1450, 80, 1450. When you break down the data, you see, oh my gosh, there's ultimate fragmentation and movement of people across the plains. Because one thing that we can use these for is not only these clustering dispersion dynamics, but we can actually see folks moving across landscapes. And we're writing up that paper right now for American Antiquity. He's actually in the PhD program at Boulder. I'm very, very proud. And he's also the head of his museum, his local museum in his tribe. So going back and serving his tribal leadership. The next study is relevant to the Great Basin work. And this is a huge result, potentially. And it's this. So the Fallon Paiute Shoshone have a story that the Lahontan Basin around 8,000 years ago, 9,000 years ago, is a sacred landscape. And people weren't living there. Well, our records, if we just willy-nilly use these radiocarbon dates, didn't think about their bias, we didn't even think about the context of the sites, we just grouped them all together. We'd say, oh wow, there's humans on this landscape. What we've done, and this is a paper we're writing up for Prestige the National Academy of Sciences right now, because we feel like it's the coolest result I've ever been a part of. And this is that. What we realize is that when we break down the site types and where these radiocarbon dates come from, these are all burial sites. And we see populations come in 11,000 years ago to 9,000 years ago, and these are residential sites. But then the residential sites drop out. And we actually have confirmation of these stories of sacred landscapes. Now, the tribe is very interested in working with us because we are extending their cultural rights over areas of land, right? And so that's how you meld these relationships, right? You have got to start with humility, going to folks. And it's not only humility in how you do your work, your research, but it's also the humility in approaching your students. My students are not going to approach my science the way that I do. It's just highly unrealistic.
You mentioned something earlier about different techniques you might be using in the lab and training students after field school or during field school after the field of art. Then I have another question about the variation in the Snake River Plain, Hawaii uplands. I mean, it seemed like there was a little bit of an increase and a decrease, but it was still within the confidence interval.
Yeah.
Is that?
So do you want me to answer that question first?
Whichever first, I don't.
I mean, that's pretty easy to answer. We can go to that. Again, this is where when you use like fair statistical measures, right? Like you can start to, so I think if I increase, are you talking about that right there?
No, in the box.
In this box?
Yeah.
Yeah, so I think if I decrease that to 500 to 100 Monte Carlo simulations, it might be significant. And I think that's why we do a lot of sensitivity studies with this, right? So sensitivity analysis is really important in what I do because you have to be able to kind of work out, okay, at this point we start to see significance and not, and so we should be very careful with this. What scares me about this decline is this a real sharp peak and this is a real sharp trough? And it's probably within 100 years. Something's going on with the calibration curve that makes that spurious, potentially. But you know what? Maybe we can pinpoint that, right? Like that's something, but I want to stress, we cannot use these methods to get to that. And I think that leads me into where I can talk about the higher precision work. Does that adequately address what you're, I mean, I think right here, what's interesting about this 1,000, this is the advent of the Fremont. And I don't want to really talk too much about the Fremont. I agree with Mark Clue about this. Like, we need to be real careful about thinking about the Fremont's role in Idaho. We need to be very careful. There's been a huge debate in the 1960s, 70s about this, about the potential Fremont presence. But there was certainly some sort of interaction going on. You know, that doesn't mean that the people, but pots don't equal people. You know, and I think that's the classic sort of cliche, but there's a lot of weird stuff going on. And I think a lot of people are moving around. So we can potentially, you know, pinpoint that, I think. But we can't pinpoint that with these methods. So what we need to do is this, and you know, actually I want to bring your eyes to this because this is a power of this technique as well. So I want you to focus on this boom right here, right? So this is the Fremont. The Fremont effectively started in this period of time around 8250, you know, last until about this bust. So this is capturing these foragers that adopt agriculture, right? We've always thought, oh, they're adopting agriculture. They appear and they disappear and like, oh, what happened to them? And it's like, we got to be honest about our strategies. So a lot of our work has been focusing on this. And this is where Bayesian modeling comes in. Okay. So you have uplands, and this is where I was going to include this in the talk, but it's a little intense. So you have uplands and you have lowlands. Let's think about Owyhee Plateau and Snake River Plain, whatever. What we can do is we can use Bayesian statistics to date events that are not directly datable. So when did this site occupation begin? When was this transition in this occupation of this site? And so what we're asking, our upland sites are, we find corn in caves, right? The early Fremont, they were adopting corn. They were putting the corn in caves. We don't see houses. They're moving around. They're living their nice forager life, right? They can still maintain seasonal mobility. And in these upland sites, you know, we get large roasting features, classic sort of Fremont. And we see, right, this is the 68% confidence interval. We have a lot of noise in the size of our data set. There's about 60 data points. So this would be minimized, obviously, this noise, the more data we have. But what we're seeing is like, oh yeah, Fremont are here during Fremont time, right? Fremont leave during Fremont time. They're not building villages. They're only building villages right here from 8750 to about 1050, about 300 years. So what we can do, again, we can use these really powerful techniques through Markov chain Monte Carlo approaches. And really, these approaches I love because we use the uncertainty to our advantage. The uncertainty is a good thing, actually. And so what we see is the uplands, they were inhabited for about 920, well, most likely the 68%, you know, 1400 to maybe 1500 years. That's kind of classic Fremont. But the pit houses, the pit house villages, permanency of place, investment in community, right? Forming communities, potentially 53 years long to 230 years long. That's mind blowing. I mean, that's what our NSF, this is our proof of concept for the NSF, right? So doing field school, lots of surveys, you know, I mean, some of these upland sites, I didn't even think I'd get good radiocarbon dates, but I mean, pretty, we got lucky. You get lucky in archaeology, I guess. Well, what we did is that we need to understand the environmental constraints on cooperation. And we can't do that with just doing low precision work. So bear with me. So you see these events right here. We're dating the uplands, we're dating the lowlands, we're dating the pit house villages. We have constructed a 2,115-year tree ring record of annual precipitation variability. That's what you're seeing in this plot right here. So the black represents annual noise in the widths of these tree rings, okay? So we use these running means. I apologize, the blue running mean is not there, the 100-year running mean. You see that it's fluctuating, and then it starts to flatten, and then it starts to fluctuate again. We've always thought that Fremont terminated at this drought, right? This transition from medieval climate anomaly to little ice age. And something maybe is going on here. Well, you know, we're eye matching at this point. So what we have to do is we have to break down the periodicity of this time series. And so we're using what's called a change point analysis here. We're looking at the change in the mean of the standard deviation at 21-year intervals. So we can see changes in mean standard deviation precipitation. But this is the real powerful plot. And this is called a wavelet analysis. And on the y-axis, you see 512 years ago, or 512 years of periodicity in this curve, and 2 years of periodicity in this curve. And you're focusing on the black. Black are significant wiggles in this curve. 8 years ago to 2 years ago, that's El Nino. This is the northernmost record we have for El Nino events in North America, in Western North America. 512, you're not seeing much black, right? Black, significant change, significant change. Well, let's think about how humans adapt to climate change. 5 generations ago, I don't know what my great-great-great-great-great-grandparents, they didn't determine my resiliency or vulnerability to climate change. But you know what? My grandparents did 3 years ago, or three generations ago. And that is my memory. That's my cognition of how I respond to climate change. Look at that, 32 to 16 years, multi-generational, multi-decadal change. You see no black right here. Adoption of agriculture occurs within major change. If you're a forager and you're worried about your surpluses, of course you're going to adopt maize, right? Like, it's predictable. You got a surplus. So lots of change. Hey, let's adopt agriculture. Let's not build villages. Let's only build villages when we don't see multi-decadal variability. Right? We can predict what our yields will be. Right? For inequalities, incipient social hierarchies, whatever, you need to be able to predict what your yield will be to be able to wield it over other people. Look at that. Significant variability on either side of the villages we've identified. Significant variability, end of Fremont. So again, this is how we use these large scales, spatial statistical analyses, time-space analyses. We're honest with the scales that they work at, where they don't work at. And when we see that wiggle that you mentioned, John, we need to use these kinds of methods. And I think this is where there's tons of low-hanging fruit in the Snake River Plain and the Owyhee Plateau.
I don't have the schedule. I think we have something at 10:30.
Hi, this is Paylin. Can people hear me?
Yeah, I would. I could always show you sites. I mean, if you want to know about the big $1.6 million DICES, I could talk about that or whatever. I mean, one thing this is the NSF, the archaeology. What we're doing is looking at the relationships of stream flow to the development of. You need to develop hierarchies. You need long-lived populations. You need permanency of place to be able to grow your population, right? And the idea is that Northern Colorado Plateau, we don't see complex Fremont sites. Eastern Great Basin, we do. Why do we see those great sites? Well, these are basin range structures. There's lower basin sensitivity. So your fields aren't going to be washed out, right? So this is melding tree ring, right? Analysis with GeoArc. This is the training we do in the field. So I won't go into the hypotheses. I mean, the first one is higher collective intelligence increases the ability of social groups to change their behavior when confronted by a disturbance regime. So let's think about that wavelet plot. El Nino events, multi-decadal, centennial scale, can't really predict 512-year spans. Well, what we're doing is that our students play a game. These are my colleagues. There's 5 PIs on the project. Students, basically, this yellow these are infrastructures built down. How do students cooperate with each other? The idea is that the more rigid you are in your infrastructure, the more vulnerable you are to changes that you can't predict. And we're doing this in the radiocarbon or in the archaeological records. So our colleagues from South America and this People 3000 project, we're comparing the Levant, the Titicaca Basin, Lowland Maya. These are highly built environments, right? The crashes are huge there. The crashes, Northern Patagonia, Eastern Great Basin, they're not that bad, right? They weren't locked into a physical infrastructure. So we're testing this. We're using natural experiments and marrying them with these behavioral experiments, trying to, I don't know, we'll see. So yeah, but this is ultimately, you know, why I wanted to start with People 3K is like, we're really, these are all of our colleagues and where we work and what we do.
I think there might have been a question coming from the Zoom audience.
Can you pull
Let
it?
me answer any question.
Just want to, this is our data set, 273,000 radiocarbon dates from around the world. And this is our interface that we're creating. So
There's a question in chat for you. I could read it or. So it's from Kaylin. I'm wondering about the issues of reproduction and mobility in your considerations of rapid hunter-gatherer population growth. Really short birth spacing is tough on mobility.
wondering about the issues of reproduction and mobility in the considerations of rapid hunter-gatherer. I mean, absolutely. I mean, I think that I don't know if I'm going to answer this sufficiently because I don't know if I fully understand the question, but I mean, the way that I can comment on that, Kay, is that I think that says a lot about the relative resiliency of the Owyhee Plateau and the Snake River Plain, and why you might see the fitting of that exponential curve, because groups are able to, they don't have to move around too much to get into the uplands or the lowlands. On my drive here to the Snake River Plain, I actually thought about the Bighorn Mountains, where, hey, probably what we're seeing is that when there are droughts in lowlands, folks are popping into the uplands. And so the closer you have proximity and space, the more easily you can move your family, right? So again, you've got, birth this every 4 years or something. That could absolutely implicate what's going on. In terms of the Wyoming study, I think that I think it's affecting some of it, the mobility, but I think that what the ultimate result is showing is the lack of potential we provide to relative permanency of place of hunter-gatherers during the terminal Pleistocene and early Holocene. In the early Holocene, they're staying in areas. As the spatial analyses I showed, they're more clustered in space than we think that they are traditionally. So I hope that suffices.
All right, well, thanks, Eric. I think, here we go.